Hello everyone. In this session, we are going to discuss about the lithium-ion battery fundamentals. Here we can see lithium-ion batteries operate on the same electrochemical principle as the other batteries, but there are important differences. First, there is no metallic lithium inside a normal lithium-ion cell. This is greatly improves safety and cycle life. Lithium-ion moves between cathode and anode through a process called intercalation process. This process is highly reversible, which is why lithium-ion batteries can cycle many times. They have very low self-discharge and no memory effect, giving user flexibility in charging. However, unlike nickel cadmium or nickel metal hydride batteries, lithium ion batteries cannot be trickle charged. Even a small overcharge current can damage the cell and create unsafe conditions. Okay, now we are going to see the construction of this lithium ion battery. Here we can see a lithium ion cell consists of five main components: cathode, anode, electrolyte, separator, and enclosure. The active material sourced lithium. It is coated onto a metal foil which acts as a current collector. The electrolyte allows lithium ion to move between the electrodes. The separator is a thin porous polymer film that prevents short circuit while allowing ion flow. The enclosure protects the internal structure and prevents leakage. First, in the lithium-ion battery construction, we need to remember these five components: cathode, anode, electrolyte, separator, and enclosure. Then we are going to see how these formats are, how different lithium-ion formats are there. Okay, depend upon the form factor. There are three different cell formats: cylindrical, prismatic, pouch. What we mean by form factor? Form factor is nothing but depend upon the physical dimensions. There are three categories. Okay, cylindrical in shape; prismatic, rectangular; pouch is a one type of cell format where we can see different cell formats here. Okay, cylindrical cells like 18650 are the most common and use a jelly roll structure. Prismatic cells are rectangular and allow better packing density. And coming to pouch cell, uses laminated film enclosures and large weight and flexible, widely used in EV application. Then what are the different chemistries of lithium ions? Here you can see we have listed common cathode chemistries and anode chemistries. Depend upon these chemistries, the lithium ion cells are varies. Where the battery chemistry mainly refers to the cathode material. Okay, different chemistries offer a trade-off between energy density, safety, cost, and cycle life. For example, LCO offers high energy density but lower safety. NMC offer a balance between energy, power, safety. LFP provides highest safety but lower voltage and energy density. LTO is an anode material that offers extremely long cycle life and fast charging but low energy density. Okay, depend upon these chemistries only lithium ion cells are categorized. Now coming to implication for the battery management system. Okay, where the choice of the chemistries directly impact the BMS design. Different chemistries have different safe voltage limits. Flat voltage curves like LFP require more accurate SOC estimation methods. Different temperature tolerance affect monitoring requirements. High energy chemistries require stricter safety control. Okay, then coming to safety and abuse conditions, where lithium-ion batteries must operate within the strict limit. Overcharge can lead to the thermal runaway. Overdischarge can cause internal damage. High temperature accelerate degradation and can trigger exothermic reactions. Lower temperature charging can cause lithium plating. The BMS is a primarily responsible for preventing all these conditions. Okay, then coming to this longevity and degradation. Okay, where battery aging results in capacity loss and increased internal resistance. Okay, high temperature and extreme SOC accelerate the degradation. The BMS must manage and operating conditions to maximize its life. Okay, where state of health estimation become critical in long life systems. Now coming to this performance requirements, where an modern BMS must provide accurate SOC, SOH, and real-time power capability. Accurate estimation allow the battery to operate closer to its limits without compromising the safety. Okay, this reduces system cost and improves the performance. Then how we are going to integrate this into the system? Where in advanced system, the BMS does more than monitoring. It control thermal system, contactors, and safety relays. Okay, and it also communicate with the load device to dynamically manage the power. Okay, now here lithium-ion batteries offer high energy density and excellent performance, but they require strict monitoring and control. The battery management system ensures safe operation, maximizing longevity, and enables optimal performance. Okay, now here overall we know that whenever we are going to use the lithium ion batteries, there must be a strict compliance of the safety. Fine. Here in this session, we have discussed fundamentals of lithium ion, how the lithium ion battery operate, what is the construction, and what are the cell formats, what are the different type of chemistries, and implication of BMS, safety and abuse conditions, and longevity and degradation of lithium ion cell. How we require the performance, what is the requirement, system integration, and overall the BMS has to ensure safe operation and maximize the longevity. In next section, we are going to explore the measurement of battery parameters. Thank you.